All right, let's say we are asked to use Riemann sums to approximate an area. So we're given a rate of y equals 2x plus 1, and we want to approximate this area where between x equals 0, x equals 4, and y equals 0, which just simply means above the y-axis. All right, so again, it's very important that you're clear when we start to do these that this is the derivative, this is the rate. So what you're finding is a total, an amount. Okay, so let's just graph it first to see what this actually looks like. So 0, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. And from here, I can see that I'm looking at my function up here. If x equals 0, 2 times 0, 0 plus 1, I'm at 1. If x equals 1, I'm at 3. And then so on. And so I continue to do these at 5, at 7, and 4 times 8 plus 1 would be at 9. So I'm looking at this line right here. Ooh, you're pretty good, drew that straight line. You know when you don't go through the dots, you just make your dots bigger, right? That's a little trick I taught you right there. All right, so what we're looking at is what is the area underneath here. And you can't just, well, in this case, being a straight line, we're going to get to things with curves that you're going to have to, see more of an exact value. So what we do with these Riemann sums is we create rectangles, okay, to estimate, to approximate this area. So say, for example, if I started right here at 0 and I drew a rectangle, then I went to the next one. I mean, you could kind of already see that our approximation is going to be wrong, right? Because this space in here is error. Okay, so that's my actual error space in there. But this might be good enough. If we have a rate, we don't actually, you're going to see later, sometimes you don't even have a function, that you just have a table of values, which brings me to, typically, that's what I will do, is I will create a table showing that my x values and my y values, so 0, 1, 1, 3, 2, 5, 3, 7, and 4, 9. So I'm gonna come back to this table here in a second. Now, hopefully some of you looked at this and you thought, well, why did you start at 0? Like if you're in the interval from 0 to 1, some of you may have started at 1 and drew your rectangles like this. So I'm hoping it's kind of clear to see that, that was an ugly one, that it's clear to see that what would be an overestimate versus what would be an underestimate. I mean, I'm under the graph, right? And so by looking at the actual table now, if I want to find the area, okay, of the underestimate, well, how do you find the area of a rectangle? You take each width here, you're taking each width times each height. So the y is the height, and then our what we call our change in x, which is by 1, is our width. So if I wanted to do this underestimate, find the area, I would take the width times the height plus the width times the next height plus the width times the next height. And notice where, Notice where I'm going to stop. So I'm not doing the next one. Why? Well, go back here and look at this graph. So that's this one, all right? And so I can see my y values at 1, at 3, at 5, and at 7. That's my underestimate. So if I add all of these up, multiply, add all these up, I get 16. Now most of the time you will see people write the width, because the widths are all the same. Basically you're factoring in out, and you're just adding those y values. Same thing, just easier to write that way. Okay, so now let's say we want to look at the area, our overestimate. Okay, so that's now these rectangles. And so as you can see by looking at the points, I'm actually starting 1 over, right? I'm starting at 1. And so usually I'll tell students, something like this, you might show with the table, this is your lower. And now we're going to move to our upper, where we're actually starting 1 over. And so I can do the same thing. I can multiply each one of these. I'm going to do the shortcut and say the width. But now I'm going to start at 3, 5, 7, and I'm going to add the 9, and I get 24, which clearly this is higher than 16, so it's an upper estimate. So this is a way that Riemann sums you can approximate with rectangles. And where we're going to go eventually is we want to be able to first say, well, this is a sum, a summation. Could I write this in sigma notation? And the answer is yes. So if I have my function and my x, I'm going to call it I, my index that is going to be moving. Think about this lower estimate. I started at my x equals 0. So I equals 0, and then what I stopped at 3 for my x values. Think of x. And then the same thing here is I started now at 1, okay, for x, and I went all the way to 4. Because eventually what we want to get to is the calculus where we take this limit and we're going to make these rectangles very, very skinny. Very, very skinny to the point where we're finding exact area. So there's 2 ways to say that. We could say we're making the change in our x get really, really small. Or, as you're going to see, how many subintervals are there? 1, 2, 3, 4, or most students will say the number of rectangles. So we call that n, our number of subintervals. And we're going to want to make that to go to infinity. And this is the more typical way you see this written. And again, what does that mean? That means I'm going to have a whole bunch of rectangles. How many am I going to have? An infinite number. Well, why would I do that? Because now notice what's happening. I'm getting exact area underneath this curve. And that's where we're going to be going with this. Sometimes I will say it's beneficial to, write out sigma notation because it might be faster than writing out an entire table. Sometimes doing a table in the beginning shows you, I think, what you're actually doing. So it kind of benefits you with that.